digital conversion. As you all know, all sensors produce the signals in analog form, but our computers and all the new technology systems are working on digital signals. So it is necessary to convert the analog signal into digital form, and the device used to convert this analog signal into digital is called as the analog to digital converter. We will discuss about necessary steps in A to D conversion, and then we will discuss the factors affecting A to D performance, and after that we will see the different types of A to D converters. Before going into different parts of A to D conversion, let us know why it is needed to convert analog into digital. As I have discussed that real signals, the voltage measured with thermocouple, speech signal recorded with microphone, all are analog quantities. They vary continuously with time. And for the systems like computers, we need to convert into digital form. Like this, I will create a sensor here. This sensor is giving me analog signal, and it has to be given into ADC to convert into a digital form. Okay, then this signal is given to digital signal processing unit, and then that signal can be given to memory. It can be saved in the memory or it can be displayed somewhere else. If we want to interconnect, give the signal command back to the actuator, again we have to convert this digital signal from the computer into analog form. Then we need digital to analog conversion, and this digital to analog conversion will be given back to the actuator. This is the block diagram how a system works. Okay, let us discuss about analog signal and digital signals. Continuous waveform, it varies with time, are called as the analog signals, whereas digital signals have some values at different levels and they are not in continuous form. To convert this analog into digital form, we have two major steps. One is sampling. We will take small values from the signal, and after taking these values we will do the quantization. So the major two steps are sampling and then quantization. Okay, so sampling refers to take values at different time points from the continuous analog signal, and this sampled values is given to sample and hold circuit, which holds the value till a new input comes up. We have thousands of samples, but suppose we have a digital signals of a 3-bit, so we have to quantify these different samples into those fixed digital values of 3 bits. It is called as quantization. So we decide how much values we have to convert into some particular levels. That is called as quantization. An important part is the sampling rate must be greater than the twice of the maximum frequency component in the signal. It is called as the Nyquist criteria. So quantization is something like that. When we have taken the samples, we decide some sample as a 0. From here to here, if any kind of value is coming, it will be considered as 0. Okay, then from this point to this point, if the values are coming, it will be considered as the value 0, 1. Then we define the third level as 1, 0, and the last level as 1, 1. This is for the 2-bit. Okay, so this is called as a quantization. The values in between these levels will not be considered with different values. the all values will be translated into in these particular levels only. Now the performance parameter of ADC, the factors which can affect the performance of ADC. Number first factor is resolution. It is defined as the minimum number which can give a change in the output, or you can say defined as the number of different digital output state which can be provided by A to D converter, or we can say that it is the ratio of V input of full scale divided by the 2 raised power n minus 1, where n is the number of bit in which we have to convert the digital signal. Okay, so resolution can be 2 raised power n, that means change in 1 LSB, or it is defined as the ratio in the input voltage needed to change the digital output by 1 LSB. Then another performance parameter is quantization error. Quantization error it is unavoidable uncertainty about the exact value of input. That means the uncertainty in the value we cannot predict, it is plus half of the LSB or minus half of the LSB. So that small amount of error is called as the quantization error. Okay, it is generally plus minus of half of LSB value. Third factor is the conversion time, which matters in high speed processing units. So it is defined as the total time required to convert an analog signal into digital output, and it depends on conversion techniques used and majorly the propagation delay of the circuit components. So the companies try to reduce this propagation delay and do conversion as fast as possible. Now let us move on to the type of analog to digital conversion. There are generally 4 to 5 types of ADCs. We will discuss here 2 types: successive approximation type. Successive approximation. As the name suggests, we are successively doing some approximation of the value using some circuit, and that approximation of the value will be considered as the digital input. Another we are going to discuss is a flash type ADC. Okay. Other than this, we have single ramp type, dual slope type, sigma delta type of ADCs also. Moving to the successive approximation digital to analog conversion, let us first discuss the op-amp, operational amplifier working. What op-amp does is, it is generally a 3-terminal device. Input terminals are called as inverting terminal like this, and non-inverting terminal plus like this, and we have third terminal is known as the output terminal. So we provide input here and here, inverting and non-inverting terminal, and we get some output here. This output depends on the input and the components we connect in between input and the output like this. These are called as the feedback components. So generally the factor by which input is converted into output is called as the gain of the amplifier, gain A. Okay, and when we are connecting input here, V in here, and we are grounding the non-inverting terminal to the ground, we get the gain as RF upon R into V output, where R is the input resistance. Input resistance. Okay, so this formula will help us to make the analog to digital conversion circuit. Let us see how we will do the successive approximation ADC. So let me draw the block diagram. I have analog input and I have given this analog input into successive sample and hold circuit. This is sample hold amplifier. So it samples the analog signals and saves the sampled value for some prescribed time. We send this value to the comparator. This comparator takes the comparison value from somewhere else. This is a threshold value. Okay, and whenever the input crosses this threshold value, it gives an output high, otherwise it will give an output low. So this is a comparator. So after this output is given to successive approximation register to save those values. Okay, and this successive approximation circuit has some control signals like start of conversion signal, and we have end of conversion signal. Okay, and we get digital output at this end, defined by the number of bits, how many bits we are using and converting that analog into digital output. This output is given back after converting into D2A converter, and this is value is given to the threshold value. This is the circuit diagram, or you can say the block diagram of successive approximation A to D converter. How it works? Suppose analog input is 6.428 volt and reference voltage I have taken as 10 volt. So I have MSB at 5 volt. Okay, the middle value is 5 volt. So I will compare the value with this, the central value 5 volt. V input is greater than 5 volt. If it is yes, then I will make the first MSB as high. If this value is greater than 5 volt, I will take first MSB as high, that is 1. Then at the second level, I will compare the input from 5 volt to 10 volt and I take the middle value as 7.5 volt. And I will check if my input 6.428 is greater than 7.5 or not. It is not greater than, it is smaller than, so the second bit will be 0. Okay, now I will look the value between 5 volt and 7.5 volt, and in between these two values I get 6.25. Okay, I will compare 6.428 with 6.25. Is it greater than 6.25? It's yes. Then the next bit will be high. Okay, now I will check the value from 6.25 to 7.5, and the middle value comes up to be 6.875 volt. And I will compare this value with my input 6.428. Is it greater than 6.8? No. So the fourth bit will be 0. So this way my value, analog value, is converted into a 4-bit digital value. I am successive approximating at each stage and converting that value. So I have taken this value for further 4 bits only. If we go further, if we want to convert it into 6-bit and 8-bit, we have to do further successive approximation and we will get the further bits also. Okay, so this is the working of successive approximation. The advantages for SAR A to D converter are: it is a low power, it has high resolution, it has small die area and low cost, and there is no pipeline delay. Whereas we have to trade off with lower sampling rates, but typical applications are in instrumentation, industrial control, and data acquisition. So we will discuss next A to D converter in the next lecture.